Isaac Newton, the father of modern science. Known for his groundbreaking work in physics, mathematics, and astronomy, Newton's contributions have left an indelible mark on the world of science. Isaac Newton was a brilliant scientist whose curiosity and intellect knew no bounds. His work laid the foundation for many scientific principles we take for granted today. He lived in England a long time ago, during a period of great scientific discovery and innovation. The 17th century was a time of change, and Newton was at the forefront of this transformation. Newton changed the way we understand the universe. His theories on gravity and motion revolutionized our comprehension of how celestial bodies interact and move. He was born in 1643, a time when the scientific method was just beginning to take shape. Newton's early life was marked by a relentless pursuit of knowledge. Newton discovered the laws of motion and gravity, famously inspired by the falling apple. These discoveries were pivotal in the development of classical mechanics. These laws explain how objects move and interact, forming the basis for much of modern physics. Newton's three laws of motion describe the relationship between a body and the forces acting upon it. Newton's work laid the foundation for modern physics and astronomy. His insights into the nature of light and optics further expanded our understanding of the universe.
Newton's discoveries extended beyond physics. He was also a prolific mathematician. He made significant contributions to mathematics. He developed calculus, a powerful tool that allows us to understand and describe change and motion in a precise way. Calculus is a branch of mathematics that deals with rates of change and the accumulation of quantities. It is essential in fields ranging from engineering to economics. It helps us understand change and motion, providing a framework for analyzing dynamic systems in nature and technology. Newton's work continues to inspire scientists and thinkers today. His methods and discoveries remain a cornerstone of scientific education and research. His legacy shapes our understanding of the cosmos, influencing everything from space exploration to the study of fundamental forces in nature.
Force is a push or pull. It makes things move or stop. Imagine pushing a swing. Your push is a force. It makes the swing move. Now imagine catching a ball. You apply a force to stop it. Force is everywhere. It makes the world go round.
Inertia is the tendency of an object to resist changes in motion. Objects at rest tend to stay at rest. Objects in motion tend to stay in motion. Inertia is like a stubborn friend. It wants to keep doing what it's doing. Newton's first law of motion, often referred to as the law of inertia, is a fundamental principle in physics that explains the behavior of objects in motion and at rest. It states that an object will remain at rest, meaning it won't move from its position, or it will continue moving at a constant speed in a straight line, maintaining its velocity. That is, unless acted upon by a net force which can change its state of motion. Imagine a book on a table. It remains stationary, not moving an inch. It won't move unless you apply a force, like pushing or pulling it. This resistance to change in motion is what we call inertia.
Now think of a soccer ball rolling across a field. It starts to move when kicked. Once in motion, it will keep rolling at the same speed, not slowing down on its own. It will move in the same direction, following a straight path. This will continue unless a force acts on it, altering its motion. The force could be friction from the grass, which gradually slows it down, or a player's kick, which changes its direction and speed. Newton's first law helps us understand why objects behave the way they do, providing a foundation for further study in physics and engineering. This law is not just limited to everyday objects but also applies to celestial bodies, like planets orbiting the Sun, which continue their motion due to inertia. Understanding inertia is crucial for students and scientists as it explains a wide range of phenomena, from simple movements to complex systems. For instance, when you apply brakes in a car, the car stops because the brakes exert a force that counteracts its motion, overcoming inertia. Similarly, pushing a heavy object requires more force to overcome its inertia compared to a lighter object. In summary, Newton's first law of motion, or the law of inertia, is a key concept that explains how and why objects move or stay still, influenced by forces acting upon them.
Section 4. Unveiling Newton's second law: force, mass, and acceleration. This fundamental principle is a cornerstone of classical mechanics and helps us understand the relationship between the forces acting on an object, its mass, and the resulting acceleration. Newton's second law of motion describes how force affects motion. It provides a quantitative description of the changes that a force can produce on the motion of a body. It states that the acceleration of an object is directly proportional to the force applied to it. This means that if you increase the force applied to an object, its acceleration increases proportionally. It's also inversely proportional to its mass. In other words, the greater the mass of an object, the less it will accelerate in response to a given force.
In simpler terms, the harder you push an object, the faster it accelerates. This is because the force you apply is directly influencing its motion. The heavier the object, the slower it accelerates. This is due to the object's mass resisting the change in motion. Think of pushing a shopping cart. When the cart is empty, it has very little mass. An empty cart is easy to push. You can apply a small force and it will accelerate quickly. A full cart requires more force to achieve the same acceleration. The increased mass of the full cart means you need to exert more effort. This is because a full cart has more mass. The greater the mass, the more force is needed to change its motion.
Newton's second law is often expressed as F equals ma. This equation succinctly captures the relationship between force, mass, and acceleration. F is force, m is mass, and a is acceleration. Understanding this equation allows us to predict how an object will move when subjected to various forces, making it a powerful tool in physics and engineering.
Section 5. Newton's third law of motion. Action and reaction. Newton's third law of motion states that for every action, there is an equal and opposite reaction.
When you push against a wall, the wall pushes back on you with the same force. This is why you don't go through the wall.
This law is also evident in swimming. When you push water backward with your arms and legs, the water pushes you forward. Rockets work on the same principle. The rocket expels hot gas downward. This propels the rocket upward.
Newton's third law explains how forces interact in pairs.
Section 6. Momentum and impulse. The science of motion. Momentum is a measure of an object's motion. It depends on the object's mass and velocity. A heavy truck moving fast has more momentum than a small car moving slowly.
Impulse is the change in momentum of an object. Imagine hitting a tennis ball with a racket. The force you apply over the short time of contact is the impulse. This impulse changes the ball's momentum, making it move in the opposite direction.
Section 7. Conservation of momentum. A fundamental principle. The principle of conservation of momentum states that the total momentum of a closed system remains constant. In simpler terms, momentum is neither lost nor gained in a closed system.
Imagine two billiard balls colliding. The total momentum before the collision equals the total momentum after the collision. Momentum is simply transferred from one ball to the other.
This principle helps us understand collisions, explosions, and other interactions. These laws are fundamental to our understanding of the universe.
Section 8. Dynamics of uniform circular motion and centripetal force. Uniform circular motion refers to the motion of an object traveling at a constant speed along a circular path. But what keeps the object moving in that circle? The answer is centripetal force. This force acts towards the center of the circle, constantly changing the direction of the object's velocity, ensuring it follows a curved path. A classic example is a satellite orbiting Earth. The gravitational pull from Earth provides the necessary centripetal force to keep the satellite in orbit. Without this force, the satellite would move off in a straight line, tangential to its orbit. Another everyday example is a car making a turn. When a car rounds a corner, friction between the tires and the road provides the centripetal force needed to change the car's direction. If the road is slippery, like during rain or snow, the friction decreases, making it harder for the car to turn safely. Understanding centripetal force and uniform circular motion is crucial in fields ranging from astrophysics to engineering. It helps us design safe amusement park rides, predict planetary orbits, and even understand the behavior of subatomic particles in particle accelerators. In essence, the dynamics of uniform circular motion and the role of centripetal force are fundamental principles that help us navigate and comprehend the physical world around us.